This is lecture 13 of Condensed Matter Physics 1. And in today's lecture, we are going to solve some problems based on the lectures that we had this week. Problem 1. For electrons in a square gallium arsenide wire of width 20 nanometers, find the linear electron density at which Nx equals 2 and Ny equals 2 levels start getting populated at t equals 0. Assume an infinite confining potential at wire boundaries. So, this is the kind of mesoscopic system that we had been talking about, and what you have is a wire of square cross section. And this is 20 nanometers, and it is a long wire. So, this way it is periodic boundary conditions. However, across the wire we have electrons confined, and what we are going to assume is that these electrons are confined in this infinite box. So, all around the potential is going to infinity, and this is where these electrons are moving. Now, I want to connect this to what I did in the lecture first. Recall in that lecture 10, what I had was a wire which had a width w and a thickness t. And it was infinite in this extent. So, in this wire what we had was different energy scales. So, one energy scale was h cross square pi square over 2 mt square. The other energy scale was h cross square pi square over 2 mw square, and third one of course was these continuous levels. So, minimum energy required to fill the first energy scale was this much, and since we assumed that T was much less than W, which was much less than L, what happened was levels started getting filled here, and then they could populate the levels out here, say up to n. With the kind of densities we were dealing with, we could never populate this level. And what I had said in the lecture was this degree of freedom was frozen. So, that never came into the being. We have a slightly different case here, because what we have is that the electron is confined in a box of width w. So, both the energy scales are going to be the same, and what you have, if you go back to your quantum mechanics, energy depending on n x and n y, where I am taking the cross section to be in the x y plane, and this is going to be equal to h cross square over 2 m w square pi square n x square plus n y square. So, you have these energy bands. So, lowest energy is n x equals 1 and y equals 1. Next level, there are two of them, n x equals 1 and y equals 2, or n x equals 2 and y equals 1. And the next level is n x equals 2 and n y equals 2. So, what we want to know is fill these levels till this starts getting filled, and we want to know what is the kind of linear density we are talking about. Now, keep in mind that the total energy is going to be equal to h cross square pi square over 2 m w square n x square plus n y square plus h cross square over 2 m l square and k square, where k is the quantum number for that continuum, because the electrons can move as plane waves along z. So, if I were to explain further in this wire, the wave function is going to be a function of n x, n y and k, x, y, z, and this is going to be 2 over w sine h cross pi over, wait a minute, sine n x pi over 2 w. Is that right? Now, let me just write it again. There is sine function, and so this is going to be equal to 2 over w sine pi w over pi n x over w sine pi n y over w e raised to I k z. That is how the wave function is, and k z wave function is normalized over 2 L over L. Let me write it neatly once more. So, psi n x n y k x y z equals 2 over w sine pi over w n x sine pi over w n y square root of 2 over L e raised to I k Z. And the energy E n x n y k is equal to h cross square over 2 m w square n x square plus n y square plus h cross square k square over 2. M. This is not there. Okay. So, let me make the energy levels. Here is energy level n x equals 1, n y equals 1. Then I have two energy levels n x equals 1, n y equals 2, or n x equals 2, n y equals 1. And next I have one energy level n x equals 2, n y equals 2. As I fill the electrons in, first I am going to fill these levels, the k levels. And as soon as the energy becomes equal to n x equals 1, n y equals 2, or n x equals 2, n y equals 1, I start filling both the levels. These are the k levels. Until I come to n x equals 2, n y equals 2, and then after that I will start filling all of them. So, what we are asking is, what is the density when the energy level n x equals 2, n y equals 2 just starts getting filled. Now, technically what are these known as are sub bands. So, what you have is these levels, one band, then this band, they start getting filled, all right. So, I am saying that first I fill n x equals 1, n y equals 1 sub band, and after that if I fill it up to the level where the energy becomes equal to n x equals 2, n y equals 1 or the other degenerate level, then I start filling both the levels. So, from here onwards I am filling n x equals 2, n y equals 1 or n x equals 1, n y equals 2 sub band. And I keep filling it until I reach this n x equals 2, n y equals 2, and then start filling everything. So, what we want to know is this density until the point where the n x equals 2, n y equals 2 level also starts getting filled. So, let us now do some math. For convenience, I will make this picture again. So, I have n x equals 1, n y equals 1, then I have these two levels n x equals 1, n y equals 2 or n x equals 2, n y equals 1, and then I have this level n x equals 2, n y equals 2, and I am filling all the way up to here. These are the levels I am filling in k space. So, this energy, the top energy that is filled, is equal to the n x equals 2, n y equals 2 energy. So, E n x equals 2, n y equals 2 and k equals 0 is going to be h cross square over 2 m w square 2 plus 2 square plus 2 square, that is 8. So, that is equal to 8, and there is a pi square also, h cross square pi square over 2 m w square. I got to fill energy up to that level. So, in filling n x equals 1, n y equals 1 level, if k max is equal to k f 1, then I am going to have h cross square pi square over 2 m w square 1 square plus 1 square plus h cross square k f 1 square over 2 m equals 8 h cross square pi square over 2 m w square. And this immediately gives you k f 1 is equal to pi over w square root of 6. Similarly, I am going to have h cross square pi square over 2 m w square. Now, the next level which I am filling is n x equals 1 and n y equals 2, or the other way, it is the same thing, plus h cross square, and let us say I have k f 2 square over 2 m is going to be equal to h cross square pi square over 2 m w square times 8. And that gives you k f 2 is equal to pi root 3 over w. So, what we have found is when we fill the levels n x equals 1, n y equals 2, or the other one, then we have k f 2 equals pi root 3 by w and pi root 6 by w when I fill n x equals 1, n y equals 1 level, and this is to the level of n x 2 and y 2. After that, that level will also start getting filled. Now, note, this is in terms of energy. So, what we should say is that the levels from minus k f 1 to plus k f 1 are filled for n x equals 1 and y equals 1, and levels from minus k f 2 to plus k f 2 are filled for n x equals 1 and y equals 2, or n x equals 2 and n y equals 1. So, these are the levels we are filling. Now, rest is very easy. Let me count the number of states and number of electrons in them. So, in z direction, density of k states is equal to L over 2 pi. So, number of electrons until n x equals 2 and y equals 2 is getting filled is going to be equal to L over 2 pi. Inside I am filling 2 times k f 1 plus 2 times k f 2 times 2, because there are 2 levels, degeneracy is 2, and times 2 for spin. So, let me write what each term means. In this, L over 2 pi is the density of k points, L over 2 pi times 2 k f 1 is number of k points in n x equals 1 and y equals 1. L over 2 pi times 2 k f 2 is equal to number of k points in n x equals 1 and y equals 2, and n x equals 2, n y equals 1. And then finally, 2 times 2 is for spin degeneracy. So, we have n equals L over 2 pi times 4 k f 1 plus 2 k f 2. So, this gives you n over L equals 2 over pi. K f 1 we have already calculated was pi over w square root of 6 plus 2, k f 2 we had calculated pi over w root of 3. This pi cancels and you can do the rest of the calculation, put in the numbers, and this with w equals 20 nanometers comes out to be 5.9 times 10 raised to 8 per meter, or 5.9 times 10 raised to 6 per centimeter. So, that is the linear density of electrons that you put in this wire, that you would get n x equals 2, n y equals 2 subband starts getting filled at that point onwards. Okay. Next, remember we talked about gauge and gauge transformations in the Hamiltonian of charged particle in electromagnetic field. So, next problem concerns that. To make you familiar with what we are dealing with, show that a charged particle of charge q moving in a static magnetic field B r and corresponding vector potential A r show that a charged particle moving charge q moving has its wave function psi going to psi prime, which is equal to e raised to I q chi over h cross psi under the gauge transformation A r going to A prime r, which is equal to A r plus grad of chi r, and the corresponding Hamiltonian is h going to h prime, which is equal to h e raised to I q chi over h cross e raised to minus I q chi over h cross. solution. Before I give the solution, let me just tell you what we are doing here. If there is a charged particle moving in a magnetic field and it has certain Hamiltonian at certain wave function, certain eigenvalues, if I make a gauge transformation, the system should not really change. The energy eigenvalues should remain the same, and under those transformation, we want to show that the wave function and the Hamiltonian change like this. So, what you have right now is that the particle is moving in the Hamiltonian. H equals 1 over 2 m H cross over I grad, and since this is q, this is going to be minus q a whole square plus the potential it is moving is V r. I am going to write this as P because this is the canonical momentum. So, I can write this also as 1 over 2 m P minus q a square plus V r. Now, suppose we make a unitary transformation. U equals e raised to I q chi over h cross on psi. So, that new wave function psi prime is equal to e raised to I q chi over h cross acting on psi. Then any operator would go to O prime, which is e raised to I q chi over h cross O e raised to minus I q chi over h cross. Right. So, any unitary transformation changes that operator to the new operator, which is like this. So, what we have done is made a unitary transformation, which is e raised to I q chi over h cross, then u psi is a new wave function, then any operator goes to O prime, which is u O u inverse. And therefore, the momentum operator P will go to P prime, which is u P u inverse, which is nothing but e raised to I q chi over h cross. P is h cross over I grad u inverse e raised to minus I q chi over h cross. Notice this is a differential operator. So, this is going to act twice on this. So, this is going to give me e raised to I q chi over h cross over I grad of e raised to minus I q chi over h cross, whatever it operates on after that, plus e raised to I q chi over h cross e raised to minus I q chi over h cross over I grad. This is the operator that is going to be. Now, you work it out, operate the grad operator on e raised to minus q chi over h cross, and you get this whole thing to be, this becomes 1. So, you get P itself, and you are going to get minus q grad of chi. Therefore, the Hamiltonian, which was 1 over 2 m P minus q a square plus V r goes to 1 over 2 m, P now goes to P prime, which is P minus q grad of chi minus q a square plus V r, which is equal to 1 over 2 m p minus q a plus grad of chi square plus V r. This is h going to h prime, yes. So, what we see is that making a unitary transformation u equals e raised to I q chi over h cross is equivalent to taking a to a plus grad chi. And I could go the other way, making this gauge transformation is equivalent to multiplying or transforming the Hamiltonian and the wave function according to what we have written. So, point is proved. So, this is how you deal with gauge transformations related to magnetic field. Next problem. Recall from the lecture on Landau levels that I had said the degeneracy of each level is the flux passing through the sample divided by the flux quanta. Where does this flux quanta come from? So, in this problem, I am going to give you a semi-classical argument for flux quanta. So, for this problem, suppose a charge q is free to move on a ring of radius r. So, here is this ring of radius r and here is this charge q on it. Now, through the center of the ring, a magnetic flux phi is passed. So, what you do is you take a maybe solenoid and let this flux be phi and it is passed through the center. Show using quantum condition that phi equals n h over q. So, let us look at the solution. When you pass this flux, so d phi by dt is equal to the voltage developed and the electric field is going to be equal to 1 over 2 pi r d phi by dt. I am not worrying about the sign. Then the force on the charge is going to be q over 2 pi r d phi by dt, and the torque on the charge is going to be r times the force, that is going to be q over 2 pi d phi by dt, and suppose this is done over a time period t, then the integration torque dt is going to be equal to q over 2 pi times phi, and that should be equal to the angular momentum of particle. And therefore, I am going to have q phi over 2 pi equals angular momentum, that should be n h cross, and this gives you phi equals n 2 pi h cross over q, which is n h over q. So, flux phi takes values in quanta of h over q, which in the case of electron would become h over E. Problem 4. Again, it concerns a charged particle in a magnetic field and talks about the gauge transformation and things like those, which are directly connected to the problem we were solving, and this is taken from the book of Gervin. Consider a quantum rotor consisting of an electron that is free to rotate around z axis at a fixed radius r. Its moment of inertia I equals obviously m r square. A magnetic flux tube containing flux phi equals beta phi 0, phi 0 equals h over E, the flux quanta is placed on the z axis, so that the Hamiltonian is h equals h cross square over 2 I 1 over I partial with respect to phi plus E r over h cross a phi square. This is I here. So, part A, show that choosing a gauge in which a phi is a constant yields E r over h cross A phi equals beta. Remember what beta is? Beta is the number of quanta that we are putting in. So, just to recap, I have an electron that is free to move in this circle of radius r, and I am putting in a flux phi equals beta phi naught, and we are choosing A phi to be constant over this circle. Then I want to show that this gives you E r A phi over h cross equals beta. So, solution: flux phi is equal to B dot dA over the cross section, and this can be written as integral A dot dl over the path surrounding that tube. And for the path of radius r, since A phi is a constant, this is going to be A phi times 2 pi r. And therefore, A phi times r is equal to phi, the flux, divided by 2 pi. If I now multiply by E, divide by h cross, I will multiply here by E, divide by h cross, this becomes equal to phi over h over E, which is given to be beta. So, if you choose that A phi is a constant over this path, then this relationship is satisfied. Part B: find the eigenfunctions of H and show that they are completely independent of phi, and find the corresponding E. Solution: you are given the Hamiltonian to be h cross square over 2 I, 1 over I d by d phi, plus, due to what we did in part A, is equal to beta square equals E psi, h psi. This is the Schrodinger equation that we are solving. So, I can take psi to be e raised to I L phi, where L equals 0, plus minus 1, plus minus 2, and so on, for keeping psi phi equals psi phi plus 2 pi. That is the boundary condition. You substitute this in and you get h psi equals h cross square over 2 I 1 over I d by d phi plus beta square acting on e raised to I L phi equals h cross over 2 I L plus beta square. where L equals 0, plus minus 1, plus minus 2, and so on. So, for this electron on this ring, with flux phi passing through the center, we get psi equals e raised to I L phi, and the corresponding energy equals h cross square over 2 I L plus beta square. So, the wave function is independent of what flux is going through, but energy certainly depends on the flux through beta. Part C. Show that the energy spectrum is periodic in beta with beta equals 1 with period 1. Solution. So, we found that the energy on L depends as h cross square over 2 I L plus beta square, L equals 0, plus minus 1, and so on. So, you have this energy spectrum which is going like this. This gap is constant. Now, if I change beta to beta plus or minus 1, all that is going to happen is going to shift by 1. But this entire spectrum remains unchanged. If somebody changes beta by 1 or 2 or 3, you come back and start measuring things, you will see that the energy spectrum remains the same. It has just shifted up or down, but you wouldn't know when you measure it. So, the spectrum is periodic with period 1. And what that means is that if flux is changed by phi 0, the system comes back to itself. The system comes back to itself. So let me just go over the argument once more. We had the energy which is equal to h cross over 2 I. This I somehow today I am writing in a messed up way all the time. L plus beta square, and if beta is changed by an integer, which implies phi changed by n times phi 0, then the system is identical to the previous system. So, energy spectrum does not change. System comes back to itself. And if you recall, this was used in giving Laughlin's argument for integer quantum Hall effect. So, that is the importance of this problem. There are two parts of the problem left, which I will give as the assignment problem. And finally, for today's problem, I am going to go back to Landau levels, and what I want you to do in this problem is calculate the energies of an electron moving in a plane perpendicular to a uniform magnetic field B using Sommerfeld-Wilson quantum condition. So, this is again coming from a semi-classical theory to calculate the energy of an electron moving in a uniform magnetic field. What are the Sommerfeld-Wilson quantum conditions? That is integration P dot dl over an entire closed orbit is equal to NH. That is the condition. Now, in this case, P is equal to m r dot minus E A. Which is m v minus E A. So, if I want to apply this condition, what I have is integration of m v minus E A dot d l over the closed path should be equal to N H. What is the closed path? I know if there is a magnetic field B like this, the electron moves in a circle. Let us say this radius is r, which I can find out later. Then I have integration m v dot d l minus integration E A dot d l is equal to N H. V is a constant when it is moving in a circle. So, I am going to have m whatever V is, and d l integrated over will give me 2 pi r minus E A dot d l is the flux. So, that is going to be B times pi r square, and that is N H. That is the quantum condition. Now, I also know that m v square over r is equal to E v b. This gives me m v equals E b r, and therefore, this quantum condition becomes 2 pi E b r square minus E b r square, and there is a pi is equal to N H, or pi E b r square equals N H. And therefore, r square is equal to N H over pi E b, which I can write as N H cross times 2 over E b. So, the radii are quantized as square root of n, and the energy of the particle E n is going to be 1/2 m omega c square r square you substitute this n and you get this to be equal to n h cross omega c. So, applying the Wilson-Sommerfeld quantum conditions, you get the energy spectrum, which is like harmonic oscillator spectrum separated by h cross omega c, and these are different Landau levels, which we had obtained earlier by solving the Schrodinger equation. So, let me now conclude this lecture by stating that we have solved problems related to 1, filling of subbands in a quantum wire, 2, gauge transformation A going to A plus grad chi, 3, energy levels of electron on a ring surrounding a flux tube, and a corollary of this was system coming back to itself when phi was changed by n phi 0, and finally, we got Landau levels through semi-classical quantum conditions. Thank you.